Okay, let's unpack this. Think about silicones for a second. We use them in, well, just about everything.
Everything. The seals in your car's engine, the tubing in a hospital, even the casing that protects your phone.
Exactly. It's this sort of invisible backbone for so much of modern life and high-performance manufacturing.
It really is.
But have you ever really stopped to think about what it takes to actually make this stuff? I mean, we're talking about high heat, very complex chemistry, extreme precision.
And doing it all at a massive global scale.
Right. And not just doing it, but doing it while meeting the absolute highest standards for environmental protection and worker safety. That's the intersection we're diving into today.
It's fascinating because you have this intense industrial hazard on one hand.
And this demand for absolute operational purity on the other. So our mission for this deep dive is to dissect that incredibly detailed management architecture that's built on international standards like ISO 14001 and 45001.
And what's so interesting here is that this isn't just a binder of policies that sits on a shelf to, tick a compliance box. Right.
This is a living, breathing management system. It's designed for operational excellence, often overseen by a high-level ESG steering committee. But the goal, the unified objective, is something they call zero harm.
Zero harm. I like that. So no accidents, no injuries.
In no unmanaged environmental releases. Nothing. It's a very high bar.
It's a compelling goal, especially when, the actual process involves things like high-pressure steam and chemical catalysts. So we're really looking at the infrastructure that turns that high risk into a protective shield.
That's a perfect way to put it.
So to really appreciate the complexity of that preventive shield, I think we first need to walk through the production process itself. The production stack. It's not just one thing, is it?
No, not at all. It's a whole family of materials. And that differentiation, it really begins right at the start in research and design.
Okay, so before anything's even mixed.
Exactly. The manufacturer has to define the precise characteristics they need. Is it durability, extreme heat resistance, specific dielectric properties for electronics? And that decision determines the type of material.
Right, that's what classifies it as, say, a solid silicone, that's high temperature vulcanizing, or HTV, or maybe a liquid silicone rubber, LSR, or even a really specialized compound.
And I imagine that classification immediately dictates what happens next in the raw material preparation stage.
It does, with incredible precision. Now you're weighing base polymers and this sort of cocktail of additives, curing agents, plasticizers, pigments.
All down to a very specific recipe.
To a technical formulation that might have an extremely tight tolerance. If you get the weights wrong here, the whole batch could fail quality checks later on.
Which is just a massive waste of energy and resources.
A huge waste.
Okay, so then comes mixing and compounding. I assume this is where it all comes together.
It is, but it's more than just blending. It's a really controlled integration. This stage is absolutely critical for the material's final consistency. And it's also one of the first major safety and environmental hotspots.
Why is that?
Because the mixing requires these specialized, really powerful machines. And they have to operate in areas with strict controls for dust and chemical emissions. A lot of those fine powders and catalysts can be, pretty toxic if they're inhaled.
I see. So the product is mixed, and then it has to actually take shape. That brings us to forming and molding.
And this step really hinges on that first choice you made back in R&D. If you're dealing with that liquid silicone rubber, the LSR.
The two-component system.
Right. You're typically using high-speed, high-precision injection molding. That's for complex parts in really high volumes, like, say, seals for medical devices.
And what about the solid, the HTV?
For that, you're more likely using extrusion for things like tubes or cords, or maybe compression molding for sheets and durable gaskets.
And then the final, I guess, chemical magic happens in curing and vulcanization. Explain this step, because it seems crucial for the final properties, but also a big compliance headache.
It is both of those things. Vulcanization is where you cross-link the polymer chains under high heat and pressure. It's what turns that soft, flexible compound into the strong, resilient silicone that we all know.
And the headache.
The headache is the heat. When you heat certain silicone formulas, they can generate volatile organic compounds, VOCs.
Airborne pollutants.
Exactly. They're harmful to human health and the environment, so they require immediate and often very expensive control measures.
So even before the product is technically finished, the manufacturer is already deep into environmental and safety management.
Precisely. Compliance is woven into every single step. After vulcanization, you have the final stages: finishing, quality assurance. all requiring rigorous testing against standards like ISO and ASTM.
And then for packaging, you have to worry about the destination market.
You do. Before a product can leave for export, it has to have the right compliance labeling for, say, Europe's REACH and RoHS regulations. It's a global web of rules.
Wow. So that 8-stage process involves high heat, toxic materials, heavy machinery, and a mountain of global regulations. A simple rule book is not going to cut it.
Not even close.
Which is why this whole process is governed by those 3 integrated management pillars we mentioned: environmental, health and safety, and social, the core of ESG.
Let's start with Pillar A, environmental management. The E in ESG. The mission here is pretty straightforward. Reduce the factory's physical footprint.
So we're talking about cutting carbon emissions, dealing with those VOCs, and managing waste.
Exactly. The foundation for all of this is ISO 14001. That's the international gold standard for environmental management systems.
And how do they actually measure success against that standard? What are the tools?
A key tool they use is the life cycle assessment, or LCA. This isn't just about what's coming out of the smokestack today. It's a full cradle-to-grave analysis. It pinpoints the environmental hotspots in the entire production chain.
And once you find those hotspots,
then you implement controls. That means things like high-tech filtration and absorption systems for furnace emissions, and of course for those VOCs from the curing stage.
and I remember reading that the best practice here isn't just about filtering what you produce, but being more efficient in the first place.
Absolutely. The modern approach treats waste as a resource failure.
Mhm.
So you see these strong operational mandates to optimize energy efficiency, which is critical because this is a very energy-intensive business, and to actively recycle silicone scrap right back into the production line.
That saves money and boosts your environmental KPI at the same time.
Instantly.
But of course, none of these environmental goals mean anything if the people making the product aren't safe. So that brings us to Pillar B, Health and Safety Management, or EHS.
Right. And here, the biggest focus for an auditor is the control of acute risk. The objective is to protect workers from 2 main things: chemical exposure and catastrophic industrial accidents.
So the framework for that is ISO 45001.
It is. Applying that standard means conducting incredibly detailed risk assessments at every critical point: the mixing area, the curing ovens, the furnace. The goal is to control toxic gases at the source.
At the source, so not just relying on masks.
No, that's the last line of defense.
Yeah.
Use engineering controls like local exhaust ventilation, LEV.
LEV. For listeners who might not be familiar, what does that actually look like on the factory floor?
Imagine a very powerful, very specialized vacuum hood. It's mounted right over the spot where the chemical emission is happening, maybe where the curing agents are being blended. It captures the fumes before they can even enter the worker's breathing zone.
An engineering solution, not just a personal one.
It's always the preferred method.
And beyond that, what are some of the mandatory practical safety measures that you'd see?
Well, beyond the obvious PPE, like respirators and chemical-resistant gloves, one of the most non-negotiable procedures is lockout tagout, LOTO.
I've heard of that. Explain what it is.
It's a procedure to ensure that before any maintenance worker goes near a piece of machinery, a mixer, a press, that equipment is fully de-energized and physically locked, so it cannot be accidentally started up.
That one procedure must prevent so many serious injuries.
It prevents fatalities. It's that important.
Okay, so those first 2 pillars are very focused on compliance and physical safety. Pillar C, social responsibility, CSR. That's the one people sometimes overlook, but it's becoming a huge part of the ESG conversation.
It's absolutely vital. CSR is really about developing human capital and ensuring community well-being. The market is finally recognizing that you need skilled, stable labor for this kind of complex manufacturing.
So it's not just charity work.
Not at all. It's an investment in the operational stability of the plant. It means aligning with ILO International Labor Organization standards: fair wages, non-discrimination, structured training programs.
It makes sense. If you're making high-tech parts for the automotive industry, you need highly trained, loyal workers.
Precisely. So supporting local communities through things like education sponsorships or vocational training. That's not just good PR, it's building your future workforce. And auditors look at all of that, plus things like supply chain due diligence, all of which gets publicly reported using frameworks like GRI and SASB.
Yeah.
Transparency is the name of the game.
Here's where the rubber meets the road, so to speak. We're moving from high-level policy down to the mandatory application on the factory floor, the Safe System of Work, or SLOW.
Right.
Why is this not just a good idea, but a mandatory layer of defense in this industry?
It's mandatory because of those inherent high-intensity hazards we've been talking about. The chemical risks from peroxides, the extreme heat from curing, the high-pressure molding equipment. Any one of those could cause a serious injury if it's mismanaged.
So the SOW is the formal system for dealing with that.
It's the structured, formal system that dictates how a specific task, especially a non-routine or hazardous one, is carried out safely. It's what completes that preventative shield.
This sounds incredibly rigorous. How is it structured?
It's completely rigid, and for good reason. An SOW mandates 7 interlocking layers. It's a sequence.
10 layers. Okay.
You must start with hazard identification. That's followed by a formal risk assessment, which then determines the necessary control measures.
Then from there.
Those controls often require a formal permit or authorization to even begin the work. Then you need documented competency and training records for the person doing the job, continuous supervision and monitoring while it's happening, and finally, robust emergency control plans in case something goes wrong.
And that structure is non-negotiable.
Completely. If an auditor is walking the floor and sees a hazardous maintenance job happening, and they find a gap in any one of those 7 layers, say the permit was issued but the training log was out of date, it's an immediate audit fail.
Because it shows a systemic breakdown.
A systemic breakdown in the safety culture. Exactly.
Let's make this real. Give me an example in a high-risk area, like one of those mixing areas.
Okay, great example. The SOW there starts with identifying hazards.
Yeah.
Dust, vapors, the risk of getting a hand caught in a mixer. The controls would mandate a detailed job safety analysis, or JSA. They'd require interlocks and guards on the machinery, and probably continuous VOC monitoring in the air.
And what about the curing ovens, where the big risks are fire and heat?
The SOW for that area is all about temperature control. The hazards are high heat, fire risk, and those VOC emissions. So the control measures are strictly enforced temperature and time limits. The EHS precautions would also mandate exhaust systems that are compliant with BAT.
BAAT.
Best available techniques.
Yeah.
It means you have to use the absolute most efficient pollution control technology that's commercially available.
This raises a really important question that I think confuses a lot of people. What is the actual difference between an SOP and SOW and these precautions you're talking about?
That's a great question. Think of it this way. An SOP, a standard operating procedure, is the instruction manual. It tells the worker how to blend the material to get the right product specification.
Okay, the what to do.
Exactly. The SOW is the safety framework around that task. It tells the worker how to perform that blending task safely by locking out the power first, by wearing the correct PPE, by having a spotter.
And the precautions?
Precautions are the preemptive checks. They're the final, immediate preventive shield. They are the conditions that must be met before the job even starts. Things like checking that the GHS-compliant labels are on every chemical container, or testing the emergency stop button on the mixer before you turn it on.
So they happen before the SOWs even put into action?
They're what prevents the risk from ever occurring in the first place.
So this incredibly complex management system is only as good as its measurable outcomes, right? You have to be able to prove it's working.
You do.
So how do you verify the ESG value of all this? I assume it comes down to verifiable key performance indicators, or KPIs. Let's use carbon reduction through recycling as an example.
Perfect. This is where we shift from safety to a verifiable environmental economics. Silicone production is intensely energy-based. Most of the emissions are Scope 1, from burning fuel on site, and Scope 2, from purchased electricity.
And you can calculate that.
Oh, yeah. We use the internationally recognized GHG protocol and ISO standards to calculate the co-euro intensity for both virgin and recycled materials.
And what does that comparison actually look like? What are the numbers?
The difference is striking. The benchmark for making virgin silicone is pretty wide, but it generally falls between 3,500 and 6,000 kilograms of co-euro equivalent per ton of product.
Mostly due to the energy needed for the initial synthesis.
Exactly, the high energy needed for material refinement and synthesis. Now compare that to the recycled product.
Okay.
Recycled silicone, because it cuts out all those energy-intensive upstream processes, brings emissions way down to a range of about 1,200 to 1,500 kilograms of co-euros per ton.
So wait, that's a reduction of what?
It means you achieve an emission reduction of between 60 and 75% per ton.
Wow. That is huge. That completely changes the environmental value proposition of whatever product you're making with it.
It's a massive ESG win. And it's verifiable. It's quantifiable. And beyond carbon, auditors are looking at a whole suite of these KPIs. You mentioned safety before.
Right.
They'll analyze the LTIFR, the lost time injury frequency rate. That's a critical marker of how effectively that SLW system is actually functioning day to day.
And is there a way to measure the culture, the proactive, preventative side of things?
There is.
Right.
That's where a KPI like the near miss closure rate comes in.
Mm.
If a company encourages workers to report near misses, incidents that could have caused harm but didn't, and then shows they diligently investigate and close those cases with corrective actions,
That shows a healthy, proactive safety culture.
it shows a learning organization. Auditors love to see that. They also track the percentage of renewable energy used, the tons of kilo equivalent per ton of finished product.
Huh.
These numbers prove the system is more than just paper. It's effective.
Okay, so let's try to connect all these dots. What happens when a manufacturer is operating at maximum complexity? Let's take a company like TechLink Silicones as an example. They're vertically integrated,
Meaning they control the whole process, from raw material to finished product.
and they use every major technology we've talked about: injection molding, compressions, extrusion, calendaring, and coating.
That profile is the definition of operational complexity, and it confirms that this multi-layered ESG, HSE, CSR framework we've been discussing isn't optional for them. It's the only way a company like that can operate at that scale.
And their certifications show they have a good foundation.
We do. ISO 9001 for quality, IATF 16949 for automotive, BSCI for social compliance. They clearly have a robust system in place.
But operating 5 different manufacturing technologies under one roof must complicate that zero-harm mandate significantly.
It does. And to get from a robust system to one that is fully audit-ready at the highest international level, they have to move beyond general policies. The refinement they need is process-specific SLWs,
Meaning a different one for each technology.
a different one for each technology. The hazards on an extrusion line are fundamentally different from those on a high-pressure injection molding machine. The SOW documentation has to reflect that level of granularity.
And what about the ESG reporting side of things? We know the overall carbon reduction for recycling is 60 to 75%, but what level of detail do advanced auditors want now?
To satisfy those high-tier customers, especially the ones focused on their own Scope 3 emissions, they need highly detailed, location-specific VOC control and monitoring data. But even more critically, the carbon footprint calculation needs to be broken down by individual process.
So they need to know the COO euro of a ton of injection molded LSR versus a ton of extruded HTV.
Exactly. That level of hypergranularity is rapidly becoming the new expectation for what true operational excellence looks like.
So what does this deep dive really reveal? I think we've seen that making silicone is a detailed, multi-stage, and frankly, a high-hazard process.
It is.
But more importantly, we've learned that to do it at a global scale, you need this incredibly comprehensive layered management system that's designed from the ground up as a preventive shield against risk.
And the conclusion is, I think, undeniable. When you integrate these rigorous ISO-standardized systems, from that SOW on the factory floor all the way up to the governance of an ESG steering committee, it does more than just ensure compliance.
Right. It's not just about avoiding fines.
No. It fundamentally enhances your operational efficiency, it drastically reduces your risk exposure, it solidifies your brand's reputation, and crucially, it improves your access to sustainable capital and green financing.
It really is all about moving from a reactive mindset to a preventive one.
It is. And here's a thought for you to mull over as we finish. Auditors aren't really asking, do you have policies documented somewhere anymore? They're on the floor asking, what demonstrable steps have you taken to prevent risks from occurring today on this specific machine with this specific material?
A much tougher question to answer.
A much tougher question. And considering the intense pressure for transparency, for Scope 3 accounting, for detailed carbon reporting, how long will it be until that kind of process-specific ESG accounting, that granular data on environmental impact, becomes a mandatory requirement for every single component we buy, no matter how small or how hidden it is inside a finished product? The system is complex today, but the future demands a level of transparency we're only just beginning to grasp.